Hello everyone, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and college or university levels. If you are interested in getting some help with your homework or if you're interested in getting some tutoring, please check out the links in the description below. Cool, so I'm going to switch over my screen ASAP fast and we can start this physics adventure. Always a good time. Okay, so let's get this party started. Okay, so this is the first question that we got on the menu today, and it is asking us, an electron starts at rest 74.5 centimeters from a fixed point charge with the charge of that point charge as 200 or 0.200, negative 0.200, ignore that A, excellent circumflex, microcoulombs. Okay, so this is just a charge of that point. How fast will the electron be moving when it is very far away? Meaning like so far away that the force from the point charge is not really relevant anymore. Okay, so let's draw a diagram to kind of represent what is going on in this situation. And then once we have a diagram, we can hopefully more clearly see what's really going on here and come to a beautiful answer. Okay, so we have an electron, let's draw it like that. And we know the charge of an electron, let's call that QE, is negative 1.6 times 10 to the negative 19 coulombs. I have that memorized on the top of my dome, but hopefully you would have like an equation sheet or somehow be able to recall that this is the charge of an electron. And we know that the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Okay, so this is our electron, and these are just properties that you should be able to access about the electron, okay? And it mentions to us that it is 74.5 centimeters. So we can represent that like this. 74.5 centimeters. We could also write this as 0.745 meters. And the reason why is because we want to convert everything to base SI units. So converting those centimeters to meters will make our calculations a lot cleaner, and our units are going to be less, are going to be significantly easier to deal with if we're all in base SI. Okay, so that's the distance, but its distance is 74.5 centimeters away from a fixed point charge. So let's just call this big Q. And we know that big Q is going to be negative 0.200 microcoulombs. Another way that we can write that is negative 0.200 times 10 to the negative 6 coulombs. And the mass is not really relevant for this point charge because, well, it's fixed in place. So because it's not moving at all, we don't really need to worry about its mass, and it's not really given to us. So, you know, not something we really need to worry about. Okay, so this is all the information that we need to know to solve this question. Okay, so the main concept that we want to think about is potential energy. Right now, this electron has some potential energy. As we can see, the charges of the electron and the charge of the point charge, they're both negative. And we know that when the signs are opposite, they're trying to get close to each other if the signs are opposite, but the signs are the same. So they're trying to get far away from each other. They're saying, get out of here, get me out of here. I'm not trying to be close to someone who's too similar to me. I imagine that's how they're feeling inside. But since we know this, we know that the electron is going to be going this way. So V is going to be going this way. And the reason why we want to have potential energy relevant is because right now it's kind of like there is a repulsive force between them, and that repulsive force between them is giving them some potential energy, right? It's kind of like we have a spring and we compress the spring. There's a force between them that's trying to separate them, and that force you know, is tightly related to its potential energy. And as that force you know, starts to push the point charge and the electron away from each other, that potential energy is converted into kinetic energy. Okay, so potential energy comes from repulsive electric force between the two charges eventually all this potential energy all potential energy, PE for potential energy, becomes electron kinetic energy. Okay, so given this, we know that the potential energy has to be equal to the kinetic energy, because the question is asking us, how fast will the electron be moving when it's very far away? That means when it's so far away that the potential energy that is caused by their electric repulsion is not really relevant anymore. So pretty much all of the potential energy is going to be equal to its kinetic energy at the end. Okay? So this is the main principle, the conservation of energy. All the potential energy needs to be transformed into kinetic energy. Okay, fairly straightforward. Now let's change KE and PE to be representative of this situation. So we know that potential energy for electric forces is K, which is Coulomb's constant, little q, big Q, just to specify that we're talking about different charges, and it's all divided by R, which is the separation between them. Okay, and kinetic energy, well, kinetic energy is the same for pretty much all situations, 1/2 mv squared, where m is the mass and v is the velocity. Okay, so the question is asking us for how fast the electron is moving, which means just v, velocity. So here our next plan is the next move that we're going to make is we want to isolate the v term. Okay, so we multiply both sides by 2 and divide both sides by m. So we have 2k q, a little q, big Q, all divided by r m, and this will be equal to v squared, and well, we just square root both sides and we get v on its own. I'll write it this way, just so we can sub in our numbers as required. So put that under the root, k, 2k, little q, the big Q, r times m. Yep, fairly straightforward, all under the root. Okay, so now we should just sub in our numbers and we can find this. Yeah, fairly straightforward. So here we have 2. Coulomb's constant is 9 times 10 to the power of 9. That's nice and easy to remember for me. Lil q is going to be the charge of the electron, and here we have it written as -1.6. -1.6 times 10 to the -19. Now we have big Q, and big Q was given to us by the question, -0.2 microcoulombs. So -0.2 times 10 to the -6. And you know, you see how we have a negative here and a negative there. They will cancel each other out. They will neutralize each other into a positive. So everything will be positive under the root, which is pretty good. No imaginary numbers here. No complex numbers here, which is what we expect. R is the separation between them, and that was given by the question as 0.745 meters. 0.745. That's the R. And the mass of the electron, well, we know that the mass of the electron has got to be 9.11 times 10 to the -31. Yeah, -31. Cool. So all of this under the root. I would personally recommend that you try to do the algebra first and isolate who you want, and then sub in the numbers. So then if you do find an error, it will be a lot easier to find. It's just my suggestion. So let's run this through the calculator and figure out what this, the numerical result of this calculation is going to be. Cool. So start this up. 10 to the 9 times 1.6 times 10 to the power of negative 19 times 0.2 times 10 to the power of negative 6, all divided by 0.745 times 9.11 times 10 to the power of negative 31. Close that bracket and send it all under the root. And my result for this calculation is 2, or I'll write it back to front just so like I can get my stuff good. We have 0.53242 132 and 29. Okay, so 29 million meters per second, but now we need to accommodate our significant figures that were given by the question. So the question gives us 3 sig figs here and 3 sig figs here, so we need to convert this to 3 significant figures for the final answer. So this shall be 2.91 times 10 to the power of 7, because this is 10 million, so that corresponds to 10 to the power of 7 meters per second. And this will be the velocity, or how fast the electron is going, very far away. So, or maximum electron speed, assuming no other influences. Okay, so it would appear that we have a precisely the same calculation here with the same sig fig, so this is all good, all good. My only recommendation in response to the solution that we have here is that you should isolate the variables before you sub in any numbers, just because writing out these numbers, if you write like even the smallest mistake, like if a 9, if you try to write a 9 but it kind of looks like this, you know, it could be confused for a 4. Like these small things could really be problematic, so I recommend doing all the algebra first, subbing the numbers at the very end. But otherwise, the above solution is good. Beautiful. Big high five. Good job. Okay, so here we have the next question that we have on the menu today, and it is asking us the drawing. Well, we don't have the drawing, so we're going to have to imagine based on this information. The drawing shows a laser beam shining on a plane mirror that is perpendicular to the floor. Let's actually draw this as we read this so we can kind of keep in mind what is going on. So it mentions that we have a mirror. Let's make this our mirror representation. And they mentioned that the mirror is perpendicular to the ground. Okay. We have a laser beam that is shining on it, and the laser beam is has an angle of incidence of 37.8 degrees. Okay, so essentially what that means is, let's say we have a red laser, like this, and like this. So it's saying that the angle of incidence, which is the angle that it makes with the normal, and with a mirror, they're going to be the same. like the incoming and the outgoing have the same angle of incidence. And this angle they gave us, it is 37.8 degrees. Okay, cool. The beam emerges from a laser that is 1.1 meters away from the mirror. So this distance right here, 1.10 meters, and 1.8 meters above the floor. Okay, so now it doesn't say if the laser is pointed down or pointed up. I'm like, the question mentions that it originally came from a drawing, so the drawing would make that clear for us. But no such luck. We will need to make a guess and hope that it comes good. The final answer here that they have is 1.2 meters. So given that, we can assume, if the answer here, if we want to like be in line with that, since this is lower than the height, we can assume that the laser up here, the laser is like the top one. Okay. Laser, and this distance that is 1.8 meters. Ignore that the diagram is not to scale. Okay. How far from the mirror does the base strike the floor? Okay, so this is what it's asking. Okay, so the laser has to be above it, otherwise the laser would hit the ceiling. Okay, so I guess the laser continues to follow this path. So at this point right there, it is asking us how in the world, or what is this distance? So let's just call that D. That's our distance that we want to know. And yeah, this would be a full visualization of the question. Whoops, let's just make that smaller so we can see there. And yeah, okay, so this is a representation of the situation. So we're trying to find D, right? So using some quick geometry, we can make some conclusions. So this angle right here has to be theta as well, and this angle is also theta. The reason why is because, well, the normal of the mirror has to be parallel to the ground, because the mirror is perpendicular to the ground. So this line right here has to be perpendicular, and we know that a diagonal that goes through two parallel lines like this has to have the angle orientation like this. So like this angle right here always has to be the same as this angle. Same vice versa for these angles right here. Okay, so if we can find out what this angle is, we know that if we have the height of the point where it hits the mirror, let's call this H. We know that this makes a right triangle, right? I'm rightly sure this makes a right triangle. So given this is a right triangle, H and D, the relationship that they have with theta is tangent, right? So tan theta is equal to H opposite over adjacent. So it's H over D. Okay. Now we have two ingredients of this. Like if we were trying to solve, we're trying to solve for D, so that it's H over tan theta. We need to find an expression for H. We need to solve for H. And a very important key that we need to solve for H is that we need to find this distance right here. Let's call that X. Okay, so now that we have this X value, we should also, let's call this 1.1 meters here. Let's call that L. Wrote that in. Now, now that we have this x value, we have another right angle triangle here, and we can use the tangent because we know L, we know x, and we know the angle here, and we know that they are also related through theta. Tan theta. So tan theta is going to be equal to the opposite over adjacent. So that's x over L. And what do we know about x? Well, we know that x plus h equals 1.8 meters, right? That was given to us by the question. So x plus h equals 1.8 meters, which means that x has to be equal to 1.8 meters minus h. Fairly straightforward. So we could rewrite this as 1.8 over 1.8 minus h over L. And then we want to solve for h, or isolate, because we need the h there, isolate h. And to do that, we will have multiply both sides by L. So we have L tan theta equals 1.8 minus h. And to isolate h, we have h equals 1.8 minus L tan theta. Okay, so we have this h expression, and we have this. Combining these two situations together, and like this. So if we have d is equal to 1.8 minus L tan theta all over tan theta, this should give us the d value that we're looking for, which is how far from the mirror the laser is going to contact the ground. Okay, so we know that L is equal to 1.1 meters, and we know that theta is 37.8. So let's sub these in. So we'll have 1.8 minus 1.1 times tan 37.8 degrees, all divided by tan 37.8 degrees. Okay, so let's run this through the calculator and see what our result is. 1.8 minus 1.1 times tan 37.8. That whole thing divided by tan 37.8. And my result for this calculation is D is equal to 1.22 meters. And that seems moderately reasonable because as we can see from the diagram, we would expect it. I know not everything is to scale, but you know, it feels like a reasonable answer that is going to appear farther than the original length here. So yeah, D 1.22 meters seems reasonable. And that was all with the power of trigonometry, is how we were able to put all of these pieces together, and then everything looks good. So 1.22 meters, exactly what we got here, so that's awesome. Explanation is a little bit lacking though, so I'll leave a comment on that. Solution is good. A more visual representation of where that calculation came from would be better, as is not clear right now. Okay, cool. Okay, so this is the next question that we got on the menu today, a two-part question. Let's just address the first part on its own first, and then we can move on to the second part. So the first question is asking us, a car can decelerate at -5 meters per second squared without skidding. That just means like this is its maximum acceleration. And this was tested on a level or a flat road. Now it's asking us what would be the magnitude of its deceleration if the road were inclined at 12 degrees, ignore the A accent circumflex, 12 degrees uphill. Assume that the static friction coefficient is the same, which is pretty important. Okay, so essentially what we have here is a situation like this. This is definitely not to scale because this angle is much larger than 12 degrees, but it's just to make the point clear. So this is 12 degrees, and we have our car, vroom vroom, like this. And under normal circumstances, we would have a deceleration of -5 meters per second. So this is A, and let's just call that the brakes, because I would assume it's the brakes that are causing that deceleration. So let's call it AB for brakes is equal -0, not -0.5, -5.0. meters per second squared. But because we're going uphill, we know that gravity is also going to provide, to a certain degree, a little bit of deceleration that is also going to go down the hill. Now, gravity is accelerating straight down like this. So maybe I'll do that in red. This will be AG, which is equal to 9.81 meters per second squared. Okay, but you know, a lot of this acceleration is really just is really just absorbed by the fact that the car is like being pushed into the ramp itself. So not all of this gravity is going to be incorporated into you know, the deceleration of the car as it's going uphill. So it would be instead better if we could break this down into a coordinate system. Oh geez, that's probably not a great place to draw that. I'll redraw that. AG is equal to 9.81 meters per second squared. Okay, so instead it would be better to break down the gravitational force into components. So this would be AG, if we define our coordinate axis like this, this can be our x direction, this can be our y direction. So this can be AGX, and this will be AGY. AGY. Now AGY is not going to be relevant to this angle. I mean, AGY is not going to be relevant to the overall deceleration as felt by the car itself, because the acceleration AGY is counteracted by the normal force. Yeah, so this could be a little bit confusing. Maybe I'll draw this in a purple color. So this is AN for normal, and that's going to be equal to AGY. So the only things of relevance here is going to be AB and AGX. Okay, now to determine what AGX is, we first need to keep in mind that this angle here is also 12 degrees. So it's also going to be theta, like that. Okay, so the overall acceleration, we're just looking for the x direction acceleration. So we want, according to this tilted axis. So the total acceleration is going to be equal to the acceleration of the brakes plus the acceleration of gravity, but just the x component of it, right? So we should rewrite this, AB, we already know that as a value, but AGX, we know that, you know, seeing how this right here, this area right here makes a right angle triangle, we can see that AGX is just going to be the, you know, knowing that this angle is 12 degrees, it's going to be the opposite. So that's going to be sine of the angle times 9.8, because 9.81, that's the hypotenuse of this right angle triangle. Maybe if I draw this, that will be a little bit more clear. So we definitely have to be sine of that angle. So it's going to be sine of theta of regular AG. Now subbing in our numbers for this, AX, we shall get, well, we originally had our 5 meters per second. let's keep the signs consistent. So we're going to have negative 5.00 meters per second squared. Assuming positive is going to be up the slope. And then we have to plus, but this is negative as well since it's going down the slope. So that plus is really kind of just like a formality thing. This is going to be sine 12 degrees multiplied by 9.81 meters per second squared. Okay, so running this through our calculator, we should find the result of this. So sine 12 degrees times 9.81 plus 5, and we have a total deceleration down the slope of 7.04 actually, rounding that to 3 sig figs, meters per second squared down the slope. Negative actually. So down the slope is really just like it's kind of redundant if we have our axes defined like this, but otherwise, yeah, so we would expect this would be the new deceleration, which makes sense because we'd expect a larger magnitude of deceleration if we're going uphill, because gravity is also decelerating us. That it would be great to show that as a calculation, but yeah, cool. So part 1 is set up good, but now we got to address part 2. Okay, so I'm gonna just write this out real fast. Part 1 would be to show the result of the calculation. Okay, now let's move on to part 2 of this question. Pretty fun. Pretty fun. Part 1 was fun. Hopefully part 2 is just as fun. Part 2 is asking us, a 6,480 kilogram helicopter accelerates upwards at 0.57 meters per second squared while lifting a very heavy 1,190 kilogram car. What is the lift force exerted by the air on the rotors, and what is the tension in the cable? Okay, so let's actually draw a diagram of what's going on here. So I'm not very good at drawing helicopters and stuff, so I'll just write heli up here. And what was the mass of the helicopter? So that's 6,480 kilograms. And it is attached by rope to a car. And that car is going to be 1,190 kilograms. Cool. And we know that this whole system has an upwards acceleration of 0.57 meters per second squared. Okay, so that's the total acceleration. And yeah, so the first part of the question, or the first part of the second question, is what is the lift force exerted by the air on the rotors? So the forces that we have here is we have the rotor force. So let's just call that FR. We have, let's call this FGH for the gravitational force from the helicopter. And then we have the gravitational force of the car, FGC. And we have a tension force in the cable, but that's more for part B, so we won't worry about that too much for now. So essentially, we're trying to solve for the rotor force, and we know the net acceleration. So we want to set it up this way. So the sum of all forces is equal to the total mass, let's call it mt for total, times the acceleration, which we know is, let's call that acceleration an for net acceleration. And we know that this is going to be the result of Fr, the rotor force, minus the FGH, the gravitational force of the helicopter, minus the gravitational force of the car. Okay, so given this, we want to isolate the rotor force. So to do that, well, we just send FGH and FGC to the other side. MT AN plus FGH plus FGC is equal to the rotor force. And to write these out in full, we know that MT is going to be M car plus the mass of the helicopter, MH, multiplied by AN plus mass of the helicopter times G plus the mass of the car multiplied by G, and that is equal to Fr. Okay, so subbing in our numbers, our car mass is going to be 1190 plus the helicopter, which is 6480, times the net acceleration upwards, which is 0.57, plus the helicopter times gravity. Actually, for these two, we can factor out the g, so it'll just be a little bit easier. So 9.81 is their acceleration, and then it's going to be 1190 plus 6480. Okay, and we can actually make this calculation even a little bit more easy. Just to type in our calculator, it could be like this. So 1190 plus 6480, and that is like we factor out that this term and this term, and then it's just going to be 0.57 plus 9.81. Okay, fairly straightforward. So let's send this in our calculator and figure out what that is. 1190 plus 6480 multiplied by 0.57 plus 9.81, and this force is going to be 79614.6 newtons. And to get this into significant figures, we were given two significant figures based on this. So 2SF, we have 8.0 times 10 to the 4 to the 4 newtons. This is the rotor force of a helicopter. Okay, pretty cool. Pretty cool. Okay, so that was the first part of the question, is what is the lift force from the rotors? We got that calculation. The next thing that we need to consider is the tension in the cable. Assuming that the cable itself has no mass, which is not always true, almost never true, but we can assume that. To do this, we want to look at the car on its own. So here we have car. We know the car is going to be 1190 kilograms. And just looking at the car itself, we have a tension force and going upwards, and we have our gravitational force, FGC, FG car, going downwards. And we know that our net acceleration is also going to be that AN value of 0.57 kilograms. So to solve for the tension, we're pretty much going to follow the exact same procedure that we did here. So maybe I'll do this in a different color, like blue, if my software can be cool for a second, please. Okay, let's do this in blue. So we know that the sum of all forces, okay, I guess we're doing this in black. So the sum of all forces is equal to the mass of just the car itself. Just the car itself, right? Because in here, as we scroll up, we are just dealing with the car here. Mass of just the car itself multiplied by the net acceleration, because, well, they're physically attached to each other, so they have to have the same net acceleration. And that is going to be equal to the upwards force being positive, so that's going to be T minus FGC. Okay, and just like before, to isolate T, we have mass of the car times the acceleration upwards, the net acceleration, plus FGC, the gravitational force. And we know that this is, the gravitational force is a mass of the car multiplied by gravity, factoring out the mass, so we can get a calculation like this. Is equal to T, and let's sub in the numbers to figure out what that is. So the mass of the car, that is 1190 kilograms. AN 0.57 meters per second squared, plus gravity 9.81 meters per second squared. Okay, let's calculate that, and we can find the tension in the cable. So, so my results for this calculation has got to be 12.35.2 newtons, and also to two significant figures. We will get 1.2 times 10 to the 1, 2, 3, 4 newtons. Okay, so there's a lot less tension in the cable compared to the amount of force that the rotors are supplying, but that makes perfect sense because the rotors are pretty much the ones that are allowing that tension force to exist in the first place, and the entire weight of the helicopter as well is dealt with that. So yeah, this makes a reasonable amount of sense. Everything is good. Okay, so we don't have that solution here, but yeah. If it was here, I would assume it'd be done the same way and all be good. Solution is missing. Video answer available. Cool. Okay, so this is the next question that we have on the menu today, and is asking us, or it's presenting us a situation where we have a skydiver that is trying to figure out her speed. And the skydiver is carrying a tone generator, pretty much just a speaker that makes a single frequency of sound. The skydiver's friend, who's on the ground, has equipment for receiving the sound waves, and the skydiver is falling at terminal speed, which means that the skydiver is at a constant velocity. Terminal speed means you cannot be accelerated any farther. That means the gravitational force is counteracted by the air resistance force that is pushing you upwards, or the air friction force. So your velocity is constant, which is pretty important for this, constant velocity. Her tone generator has a steady tone of 1480 hertz, and the speed of sound is going to be constant, and it's 343 meters per second. And it's also the same at all altitudes. That's not the case in real life, but that is an assumption that we need to maintain for this question. If the friend on the ground receives waves of frequency 3,260 hertz, we need to figure out the Skydiver speed of descent. So this is the first part of the question, and the second part of the question is we're trying to figure out the reflected frequencies, but we'll get to that when we get there. Okay, so drawing out the situation, we have a person, a skydiver, like this, and they have a sound maker. And we have a person down here who observes it, and they observe it at a higher frequency. So here the F source is going to be 1480 hertz. The F ground is measured at 3260 hertz. The velocity of sound is going to be equal to 343 meters per second. And we are looking for the velocity of diver, because these are the only things that we really need for this situation. Okay, so to do this, the concept of interest here is the Doppler effect. Which pretty much means approaching things increase frequency what's the opposite of approaching? Leaving things or departing things. Have decreased frequency. Okay, so since we're approaching, clearly we're going to have a higher frequency. And the equation to model this is, let me pull up my reference right here, is that when we have, right now we have a source moving towards a stationary listener. So this is the equation that we want to use. So we have F ground, so that's the observer, is equal to F source multiplied by the velocity of sound over the velocity of sound minus the velocity of source. Okay, this is the equation that we want to use. A source moving towards a stationary listener. Yeah, exactly. Okay, so here we want to isolate V source. So to do that, we shall bring it to the other side by multiplying both sides by it. So we have V sound minus V source. And we divide both sides by F ground, so that will be F source over F ground times V sound. And we can isolate V source by switching the sides. So we can do V source is equal to V sound minus F source over F ground, the velocity of sound, and we can factor this out to make this a little bit easier to calculate. Is equal to V sound 1 minus F source over F ground. Okay, so now we can just sub in the numbers that we need and we can calculate the velocity of the source, which is the diver in this case. So the velocity of sound is 343 meters per second multiplied by 1 over the source, which is going to be 1480 hertz divided by 3260 hertz. Okay, ideally we should get something that is lower than the speed of sound itself, because we did not mention anything about sonic booms. So let's run this calculation ASAP fast. 1 minus 1480 over 3260 times 343. And my calculation for this is 187 meters per second. And that's to 3 significant figures, which is what we're given in the question here. Okay, cool. So did we get the same answer on the given here? Likely just a rounding error, but we got pretty much the same answer, so that's gotta be good. It's probably just a rounding situation. That's peculiar, but okay. Okay, so that's the part 1 of the question. Part 2 of the question is asking us if the Skydiver were also carrying sound receiving equipment enough to detect the waves reflected from the ground, what would be the received frequency of the diver itself? Okay, so this is one of those situations where the ground is going to become the source now, and the listener is going to be the receiver, or the listener is going to be the diver itself. So we're going to have a listener approaching a stationary source. So that's going to be listener approaching stationary source. So this will be part 2. So the equation that we want to start off with, and we're going to do our stuff with, listener moving towards stationary source. So listener, let's just call that FD for diver, is equal to the F of the source plus the V SOS for sound plus the velocity of diver, all divided by the velocity of speed of sound. Okay, so this is listener towards stationary source because we're going towards the ground and the ground is the source. Okay, fairly reasonable. So we are trying to find the frequency as observed from the diver, and well, we actually don't need to do any algebra for that, and we have our V source, which is our diver, as this calculation. So this is actually fairly straightforward. We'll just have our V source, which is what is bouncing off the ground, and it hits the ground at 3260, so that's going to be here. That's going to be our V source. Our speed of sound, 343 meters per second, plus the velocity of the diver, 187 meters per second. So that's FT. All divided by speed of sound, 343 meters per second. Okay, let's ask our calculator what this will give us. I expect a number larger than 3260 because, well, when things are approaching, they have higher frequencies. So That's what we'd expect here. So 343 plus 187 times 32, and my result for this calculation is 5,037 hertz, and we want to convert to 3 significant figures because that's all that we were given in the question. So 5.04 kilohertz FT. Frequency as observed from the diver for the reflected wave. So the Doppler effect, this is how the Doppler effect works in action and how you can see it work. It's pretty cool stuff. Doppler effect is very useful in many different areas, not just for sound, but also in light. And we use the Doppler effect and its interaction with light to do a lot of precise calculations about how, about like space observations. Very cool stuff. Okay, is there anything else in this question we need to address? This appears to just be the a repeated part of the question, but otherwise things are good. And came to very similar calculations. Really, it's just going to be like rounding errors, so these will both be acceptable as right. But yeah, okay, cool. So solution is good. Some concerns about rounding, but otherwise answer is good. Cool. Okay, so here we have the next question on the menu today, and it is asking us a crate of a mass 10.5 kilograms, it's fairly heavy, is pulled up an incline with an initial speed of 1.5 meters per second. The pulling force is 100 newtons parallel to the incline, and the incline makes an angle of 17.5 degrees with the horizontal. Coefficient of friction is 0.4, and the crate is pulled 4.75 meters. I'm going to assume that is like up the ramp. Okay, so let's draw a diagram for this little description of a situation right here. So we have a slope. Let's draw a nice slope. Like, let's get a straight line like this. And this is going to have an angle. Okay, I expected that to be a straight line. Okay, so this angle right here, they said is 17.5 degrees. Let's call that theta. We have a 10.5 kilogram box. And we know that it has an upwards force up here of 100 Newton. Let's call that FP for the pulling force. We know that the coefficient of friction it's going to be kinetic friction because it said it was moving. So mu k is equal to 0.400. And the crate is pulled 4.75 meters. Initial position. its initial velocity, let's call that velocity v0 for initial, is 1.5 meters per second up the ramp. I'm going to assume up the ramp because we have a force pulling it up there. So 1.50 meters per second. Cool, so this is all the information that was given to us directly from the question. Now we can do some things, make some calculations, and determine some things that are not directly given to us from this from the question. So we know that this mass on the ramp has to have a gravitational force. Everything with mass has a gravitational force. So let's make that green, gravity G, green. And that force goes straight down. But it is very convenient if we define our coordinate axis to be perpendicular and parallel to the ramp. So let's do it like this. And oops. So we can see, hopefully, that FG on its own is not perpendicular or parallel to the x and y axes that we have here. So instead we should draw its components out so we can have those to deal with individually. So this will be FGX and this shall be FGY. And we know that FGY plus FGX is equal to the total FG, and we just break it down to the components as you would often do with sloped motion type situations like this. Okay, cool. So to counteract FGY, we know that we have to have a normal force. So the normal force is going to be in the complete opposite direction. Let's call that Fn for normal, and that is equals to FGY in terms of magnitude. Because if they were not perfectly equal in magnitude, they would be either sinking into the ramp or flying off the ramp, and both of those things are not happening. And the last force that we need to consider is the frictional force, which is going to go down the ramp like this. Let's call that FF, and this is equal to mu k Fn, and this is, let me draw this. Here is going to be the same angle, 17.5 degrees. So this is just mg cos theta, and this is equal to mg sine theta. So Fn must be equal to mg cos theta. Okay, cool. And so what we want to do first is we need to find the amount of work done by gravity. Right, and we know that since this system is only moving in the parallel direction of the, it's only moving parallel to the surface of the slope itself. Okay, so given that that's its motion, we know that the work done is the dot product of the force times displacement, and we only really need to consider the FGX and multiply that with the force here, the distance that it travels, and that will give us the work. So work done by gravity. We know that only motion is sliding up the ramp, and only x component of gravity has any work. Y component, no work, because motion perpendicular. Now, what do we know about the sign of the work done by gravity? Since it's sliding up the ramp, gravity is going to try to push it down. So any work that gravity does has to be negative. So should be negative. Because opposes motion. And also you can see that FGX is going in the negative x-axis direction, so that would make perfect sense. So the work done from gravity, let's call the work done by gravity, WG, is going to be equal to the FGX multiplied by D, which is the distance that it travels. Let's call that D. Okay, so subbing in our numbers here, we have mg cos, whoops, not cos, it's going to be sine. Sine theta times d, subbing in our numbers, our mass is 10.5 kilogram. G, 9.81 meters per second squared. Sine, 17.5 degrees. Times 4.75 meters. Okay, so let's ask our handy dandy calculator what in the world that calculation is. Oh, keep in mind that this has to be negative because it opposes the motion and because the force is going in the negative direction. Okay, so that's where the negative comes from. Negative is also going to be there. And yeah, let's figure out what this is going to be. So 10.5 times 9.81 times sine 17.5 degrees times 4.75. And my results for this is the work done by gravity is going to be negative, don't forget the negative, 147 joules. It seems that we have been given three significant figures for all of our numbers, so this has to be three significant figures for our final result as well. Okay, cool. So the next part of the question is asking us how much mechanical energy is lost due to friction. And how we calculate this is going to be largely similar, except we're going to be multiplying the frictional force with the distance. Okay, so work done, it's essentially how much work is done by the friction, because all work done by friction is like the mechanical energy that is lost. So friction work should be, it will just be, let's call that WF for work of friction. That is going to be the force of friction, FF, multiplied by the distance that it travels, so FT. And we know that the friction force from our diagram is equal to our coefficient of friction times the normal force. Mu k, normal force, times d. And we know that our normal force has to be completely equivalent to the y component of our gravity force. And that is mg cos theta. Okay, so cos theta d, and yeah, that would be our calculation, and we just got to sub in our numbers. So our mu k is 0.400, our m is 10.5 kilograms, 9.81 meters per second squared, times cos, was it 17.5 degrees, times 4.75 meters. Yeah, okay, so let's run this calculation and see what we get. 0.4 times 10.5 times 9.81 times the cosine of 17.5 times 4.75. And my calculation for this was 186.65 joules. Okay, do we get the same answers here? Yep. Okay, so this person only did A and E. It would be better to address all of the questions, but it's cool. It's cool. So the next question that we want to address is part C. I would assume this is right. Well, I know it has to be right. The next part of the question is asking us how much work is done by the 100 Newton force, which is just this one. So this is just 100 newtons times the distance that it travels. That's the amount of work done. So a puller work, I'm going to assume that's like a human operator pulling this. And this is just of the pull is going to be equal to the 100 Newton times 4.75 meters that it is that force is applied over, and that's going to be well, fairly straightforward, 475 joules. Yeah, cool. The next thing is like, what is the change in kinetic energy of the crate? So the change in kinetic energy is going to be the work done by the puller minus the work done by the force minus the work done by gravity. Okay, so all of these questions are actually very tightly related. So the change in kinetic energy it is equal to let's just call that delta KE. This is going to be equal to the work of the puller minus the work done by friction minus the work done by gravity. So the work done by the puller is 475 joules minus the work done by friction, that is 186.65 joules, minus the work done by gravity, which is 147 joules. Yeah, so let's calculate that out. 147. Let me actually use the precise value that I have in my calculator still, because my calculator got RAM 0.13. So 475 minus friction minus gravity is equal to 141 141.22 joules to 3 SF is just 141 joules. Okay, so we increased the kinetic energy by 141 joules just by the work done by the puller, counteracted by the work done by gravity, counteracted by the work done by friction. Okay, cool. And the final question is, what is the speed of the crate after being pulled by 4.75 meters? So essentially, due to this change in kinetic energy, because we were originally moving at this 1.5 meters per second velocity, after we change our kinetic energy by this much, what is our new speed? So our final velocity comes from energy. Okay, so essentially we have our KE final is going to be equal to our initial kinetic energy plus our work plus our change in KE, which we just calculated in the previous question. We know that this is going to be 1/2 mvf squared, our final velocity, and it's going to be equal to 1/2 mvi. Vi is our initial velocity plus our change in KE. We can just leave that as this for right now. Let's just call that delta KE. Because it's a number, we'll sub that in after we do our algebra. So now we want to isolate VF. So we will multiply both sides by 2 divided by m, So VF is equal to, the whole thing has got to be under the root. It's going to be 2 over m, oops, not 3. Drew the m sideways. 2 over m of 1/2 mvi squared plus delta ke, all under the root. And to simplify this a little bit more, VF is got to be under the root, the 2 over m cancels out the 1/2 m here, so that's just going to be vi squared plus 2 over m delta ke. Okay, now let's sub in our numbers. So our initial velocity was 1.50 meters per second. Got to put that in the square. 1.5, yep. And then we have to add 2 over 10.5 kilograms. And this whole thing has to be multiplied it's 10.5 kilograms, and we have to multiply that whole thing by 141.22 joules. Okay, and that will give us our final velocity. And let's send this in our calculator to figure out what that is. Okay, so from the RAM, I got this. Divide by 10.5. Plus 1.5 squared. Putting that all under the root. And my final velocity calculation is 5.40 meters per second. Yeah, seems reasonable. Exactly, so 5.4 meters per second. This will be our final velocity after all of these forces. And that's fascinating. I guess the method here was done with by finding the net force and then the acceleration due to that net force, and then but I think because this person, like, the question originally asked for just to address things that are wrong, I think what happened here is this person was or this answer came from trying to do this without considering the previous one. So because of the slightly different process, there could be some rounding errors that are causing this discrepancy. But you know, when you address this question like on a step-by-step process, you should hopefully find that because you're calculating the work, like every question builds off the previous question. So given that, I trust my answer a little bit more. Okay, so this will be the final velocity of the crate, and that will be that. Cool, so let's just verify this. So part A is good. Parts B, C, D are not answered, and they help make a more clear procedure for part E. Would be easier to do with energy instead of finding the net forces / accelerations. Cool. Okay, so this is the next question that we have on the menu today, and it's asking us 2-point charges. One is 3 microcoulombs, ignore the A accent circumflex, and the other one is 6.1 microcoulombs, and they are separated by 1.4 meters. We are looking for the electric potential midway between them. Okay, so let's actually draw a diagram to represent what this situation is. So let's draw the first one. Let's make this Q1. We have 3 positive 3.2 microcoulombs and we're looking for the point halfway between them. So let's just call this R and R. Since we're halfway between, they have to be the same. And here we have Q2 negative 6.1 microcoulombs. Okay, so let's call its point of interest point A. So we're looking for the electric potential at point A. So essentially, the procedure that we want to follow here is we want to find the electric potential as caused by each one of those charges individually and then add them up. So find E potential of individual sources and add them up. Okay, that should be the way to go. The equation that we want to use for finding the electric potential we often represent it with the variable V, representing voltage, but we want to say electric potential instead of voltage because we normally say voltage more in the respect of electric circuits and electric potential in like more static electric situations like this, but we often use the letter V. Here we use the letter, I mean they use E to represent the electric field, but I actually have an easier procedure for how to solve this. This is just K Q over R. Yeah, so KQ over R. So we know that R is going to be the same for both of them. So our V at point A, let's call it VA, is going to be equal to the V from Q1 plus the electric potential from Q2. And subbing them out, we have Q1 for that one plus K Q1 over R for the second one. Okay, well, Q2, not Q1. Okay, cool. So let's sub in our numbers, and actually, before we sub in our numbers, let's do some factorization to make this calculation a little bit easier for us. So our VA, we see how K over R is common to both of them, so we can factor that out, K over R. And this shall be, what's left is Q1 plus Q2. Okay, now R is going to be half the distance between them. And because we know the full distance between them is 1.4 meters, we know that this has to be 0.7 meters. 0.7 meters. Okay, so that's our R value. Our K value is Coulomb's constant. So let's actually just start subbing in our numbers. So we have 9 times 10 to the 9 for our Coulomb's constant. R is 0.7 meters. Q1 is positive 3.2. 3.2 times 10 to the negative 6 coulombs plus, and our second charge is negative. Okay, keep in mind it's negative, and we have to have that negative associated, or that negative needs to be here. So negative 6.10 times 10 to the negative 6 coulombs And this will be our electric potential at point A, halfway between them. Okay, so let's do this quick math. So we got, in the middle we have 2.9 times 10 to the 6, 10 to the negative 6, 2.9 times 10 to the power negative 6, multiplied by 9, multiplied by 10 to the power of 9, and all divided by 0.7. So my calculation for electric potential here has to be 3. It's actually going to be negative, right? Because since this overpowers that, it has to be negative inside the bracket, and the negative, there's no negative out here to counteract that. This will be negative 37285 volts. And to adjust for significant figures, we have 3 significant figures. So we could say VA is equal to negative 3.72 times 10 to the 4 volts. And this would be our electric potential here. Cool. So that would be my final calculation. The issue here is that these are not, that should be negative, right? The original charge here was negative, and that was not included here, so this answer is unfortunately inaccurate. So this would be a better solution is negative 37,000 volts, or 37.2 kilovolts. You can write that as well. Negative 37.2 k volts. Okay, cool. So yeah, that would conclude this question. I just got to mark that the sign error. Obviously on the 6.1 microcoulomb charge, which makes the final calculation wrong. Oh man. Seems that time flies when we have fun, as the old saying goes, and we got to our last question. So those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please subscribe and hit the notification bell below. If you really enjoyed this video, please leave a like and a comment and share it with your friends. This has been Millan from OneClass. I hope to see you again soon. Today has been a fun time with the physics. The physics will never do you wrong. I had a great time. I hope you had a great time too. Have an amazing day or evening, whatever time you're enjoying this, and take care. Physics is good time.